So in this case, I want us to consider the series RLC circuit, which is also one of our revisions that you need to understand as we are working with our N4 syllabus. So remember, we worked with RLC when you are dealing with the resistor and capacitor. You worked with RL dealing with the resistor and inductor in series separately. Now they are connected together. So meaning to say, whatever that we had is not gonna change the reactance that we had of an inductor. Remember, this is 2 pi FL, that of a capacitor, given as 1/2 pi FC. This is what we had having our reactances, which are measured in what? In ohms. So with this, we do understand that the current in the series circuit is the same, meaning to say the total current that we are seeing there is the current that is going to flow across the inductor, the current that is going to flow across the resistor, sorry, the inductor, and also the current that is going to flow across the capacitor. This is the one that is now giving the voltages, the current times resistance, we've got VR, current times L, we've got VL, current times this XL is going to give us VL, current times XC is going to give us VC. So meaning to say these voltages can be determined from that total current, which is the total current times resistance. If you're dealing with VR, the voltage across the resistor, the voltage across the inductor, still the same thing, times the inductive reactance. So it's going to be IL, which is same as what? The total current. So we're just going to take this as the total current instead, times what? The reactance of the inductor. If you're dealing with a capacitor, you're going to use that reactance of a capacitor. So that's total current times the reactance of a capacitor. So these are voltages that can be determined across each component. So we're going to have this, but we need now to consider, let's say we talk of the impedance and we talk of the total voltage. Remember, those are referred as the phasor sum, the phasor sum. So the phasor sum, or whatever that you have, it is going to be considered because of the reactances that you are given. The reactances that you are given. It can be this way. So let me just write 3 possible ways that you can actually have. So we've got 3 possible conditions that can exist. Remember, from N3, we talked about this, that we can have XL being greater than XC. That means our circuit is more inductive, that is mainly inductive. That is mainly inductive. Okay. So if this circuit is mainly inductive, if it is mainly inductive, what does it mean? Remember, on an inductive circuit, when we dealt with an RL, we talked about this. Current was lagging the voltage, meaning to say the voltage was leading the current. That is the condition where we saw something like this, the inductive on top. That is talking of the voltage. You're going to have our VL this side, our VR, and the one for the total. So VL will be on top. So understanding that VL is going to be on top, it is going to help you in the phasor diagram application because VL is the major part. But in this case, whatever that you have, the XL, just going to have something like this. Okay. On your phasor diagram, you're just going to present with XL and XC when XC is greater than, which is mainly inductive. Meaning to say we consider of inductive. So in this case, you just present your XL. You also present your XC. And also, we're going to talk of the resistance. But the total impedance, because it's more inductive. So there we're going to have the difference in this case. The difference that we have here is going to be of XCL minus XC, which is the difference, which is the one that will correspond to the total impedance, which is the one that corresponds to the total impedance separated by the angle theta, because there we are talking of being more inductive. So we are going to have a circuit on top. Remember when you dealt with RL, we had this on top, but this now, this difference here is the difference, this distance that we are seeing here is the difference between XL and XC. So that's XL minus XC. XL minus XC, that is the difference that you are seeing here. That is corresponding here at this side. It's the difference of XL minus XC as our opposite to this one. So understanding this, it can help us in the calculations that XL is greater than XC. It can help us even in the calculation of the total impedance. Now, that is the phasor sum, so it's going to be the square root of, so we're going to have R squared, this one. Remember, we are talking using Pythagoras. So we've got this side, which is representing R, and this other side here, which is represented by XL minus XC. So it's going to be plus XL minus XC squared. That is where it is coming from. We've got this side. Remember the Pythagoras theorem. Given two sides, we can have the third side. So just the square root of this. It was supposed to be Z squared is equal to, then you introduce what? The square root. In the same sense, we can use it even in the voltage, because we shall be having also the voltages. This will be VC, this will be VL, then we'll be having the difference between VL minus VC. So that same concept is going to be applied on the voltage. So meaning to say also the total voltage can be calculated as the square root of, so we're going to have VR squared plus the difference. So it's going to be VL minus VC, just like XL minus XC. So this one is going to be given as VL minus VC squared. That is what you'll be having there. Talk of the theta, which is the phase angle in that case, theta. Adjacent, that is what? The resistance. The hypotenuse is your ZT. So you can simply use arc cos. Resistance over Z. Remember what I said about all series circuits. This one is a series circuit. Just use arc cos or R over Z. That one can work. Yes, you can use any other formulas. You can even opt for arc tan. As you can see, we've got the opposite. So you can use arc tan, the opposite, which is XL minus XC over the adjacent, which is the resistance. That is still is going to give us a phase angle. So I prefer that you just opt for this one, because whether it's as long as it's a series circuit, it's an RL, it's an RLC, we saw that this formula can be used anyway, as long as it's a series circuit. So this is for a condition when our XL is greater than XC. Our circuit is mainly inductive, so it's in favor of the inductive, which is opposed when now XC is greater than. In a condition that XL is less than XC, what does it mean? It means XC is bigger than what? It's bigger than XC. So it's going to be another condition where XC is now bigger than XL. The reactance across the capacitor is more than that one across the inductor. It means our circuit is just mainly capacitive this time. So it's now mainly capacitive. And what is it that we understand when our circuit is mainly capacitive? The voltage is leading. So meaning you say the current is going to be lagging in that case. When you're dealing with a capacitor. Okay, sorry, they're going to be like this. Let's go back to our CV, guys, before we confuse each other, our civil. So this is the capacitor. So the current will be leading the voltage, meaning to say the voltage is lagging. The voltage is lagging the capacitor. Okay, so you're going to have it that way. So meaning to say in our presentation, in this case, we're going to have something like this on our presentation of the phasor. Okay, just like what we had, the resistance, our XL and our XC this side, but now it is more capacitive. So meaning to say we'll be talking of the difference going down in this case here, which is the difference of XC and XL. So that difference is called XC minus XL because it's more capacitive. So you're going to have XLC minus XL, which corresponds to what? To the total impedance. So you'll be having your total impedance separated by the angle theta. So that's the condition. So meaning to say, guys, with current, guys, we know that current is in phase there. So with this condition, you'll notice that there's a difference now that is between XC minus XL, which is the one that is actually correct. This that we are seeing here is the one that is corresponding, guys, here. Is the one that is corresponding here, this XC minus XL. So if it is the one that is corresponding, it means also you can calculate our total impedance from there, the phasor sum from our Pythagoras theorem, the resistance squared plus this other side, which is XC minus XL squared. So it's going to be XC minus XL squared because XC is bigger. So you're going to subtract XC minus XL. Same with the voltage. If it was the voltage, it was going to be VC minus VL. So meaning to say the total voltage was going to be the phasor sum of VR squared plus the difference then, that's VC minus VL squared. Total voltage. Phase angle theta still can be calculated from arc cos. What is that we have on the adjacent? Adjacent, that is our resistance over the hypotenuse, which is the impedance. Or you can use the arctan because there's opposite there. So you can even use the arctan of the opposite now, which will be XC minus XL over what? The adjacent, which is the resistance. It's up to you. Opposite over to which one to use. But as you can see, series, this one, throughout, it's the same. So I prefer that if you understand that, you're going to just apply that consideration. So that is what you have in that case. These are the two cases that you are supposed to consider when they are equal now, when it is a condition that these two, they are equal, XL and XC are equal, there will be at resonance now when XL is equal to XC. This is a condition that we'll talk about on another part, which is called the resonance. So that will be the resonance of RLC circuit. So in this case, on the possible calculations, this is what you're supposed to expect. XL to be greater than XC or XC to be greater than XL. It is mainly inductive. It is in favor of what you had when you were drawing those inductive circuits when they were separate. That is what I'm simply trying to say. So you just have to check which one is bigger. Then you know, okay, it's more inductive or it's more capacitive. There we are given a question. Calculating the values in a series RLC circuit. A resistor of 25 ohms, an inductor, and a capacitor there, they are connected in series and across a 100 volt 50A supply. The question was calculate the following 1.1, the total impedance of the circuit. So as we saw that the total impedance of the circuit must be considered to say, okay, is it that XL is greater than XC? I mean, XC is greater than XL? Or we are having XL greater than XC? Which is it that we consider? So we must talk of XC and XL in that case first, all right? So 1.1, we'll need to calculate XC and XL first so that we see which one is bigger. So XL from the inductor, remember our XL, guys, does not change. That's 2 pi FL, which is 2 pi times the frequency, 50 hertz, the inductance 0.15. So that was going to give us XL, which is 47.124 ohms. I think we've been talking about, we've been using this value, guys, for a lot of questions. But anyways, that's it. We do the same thing to determine XC across the capacitor. So across the capacitor, XC, remember, 1 over 2 pi FC. So that's XC is going to be 1 over 2 pi times frequency. Remember, that's 50. Capacitance, 100 microfarad. So that's 100 times 10 to the exponent of -6 times 10 to the exponent of -6 for that microfarad. That was going to give us XC, the reactance of the capacitor, which is 31. So there you are going to obtain 31.831 ohms. So comparing these two, you have to compare now, okay, and see which one is bigger. So we can see that XL is greater than this one. XL is bigger than, this is 47, this is 31. So we can see that XL is greater than XC. So if XL is greater than XC, we are talking of a condition where our circuit is mainly inductive. That is the condition. So Z can be given from R squared plus this XL minus XC. So that is the condition there. So just consider which one is bigger there. So therefore, you can calculate our Z. That's the square root of, and I have R squared plus the difference, the one that is bigger minus the one that is smaller, just like that. So you don't even need like a lot, guys. Just know which one is bigger there. So it's going to be XL minus XC squared. Okay, so let's substitute into the formula. That's R, which is the resistance of our circuit, 25 ohms, given here. So that will be 25 squared plus the difference between these two. Okay, so that's 47.124 minus 31.831 like this. So this whole part is being squared. So that was going to give us Z, the total impedance of the circuit. And that was going to be 29.307 ohms, just like that. Okay, so guys, let us do as much revisions as we can. With the total impedance, we can calculate the total current. Remember that current from the total voltage, guys. This one is not going to change. The total current is simply the total voltage over the total impedance. So that means we're going to add this, the total voltage, which is 100. We just calculated, guys, our total impedance here. That's 29.307. So this is what you're going to have, 29.307. So this is going to give us the total current of the circuit, which was going to be 3.412 to 3 decimal places. And this is current, guys, measured in amps. The voltage drop on 1.3 across each component, because we are given now, we have the total current, remember, which is 3.142. Okay, 3.412. Sorry for that. That is 3.412 amps. So with this current, we can calculate the voltage of each component, because remember here we've got the reactances of the capacitor, of the inductor, and the resistor is also given. So that means in that case, 1.3, we can calculate the voltage across each component, okay? Across the resistor, so that is VR is going to be the total current times the resistance value. So the total current, we have it, guys, 3.412 times the resistance value, which is 25. So the product of this was going to give us VR, which is 85.3 volts. We do the same thing with this, gonna calculate across the inductor. So the voltage across the inductor, total current times XL, which is the reactance of the inductor. Are we having the reactance? Yes, we calculated, remember here. So the reactance, just going to take it. So current 3,412 times the reactance, which was 47,124. So that was going to give us the voltage across the inductor, which is 160,781. It was going to be 787, sorry, volts. You do the same thing here to calculate that across the capacitor, which is our VC. So VC, the total current, times the reactance across the capacitor. Meaning to say, total current, guys, we have it, 3,412 times that reactance across the capacitor, which we calculated as 31,831. So adding up, multiplying these two, you're going to obtain 108,607 volts as the voltage across the capacitor. So there we've got the voltage across each component, guys. The resistor, the inductor, and the capacitor. These are the three components that we are having. Then after that, they want you to determine the impedance phase angle. As I said, guys, dealing with the resistance and the total impedance is one of the easiest because you just use the arc cos. So if you want that, because it is, okay, we saw that this one, it's a XL is greater than XC. XL is greater than XC. So you can also use this one of arctan XL minus XC over R. It's up to you. Or you just use the one that is the universal formula for all series combinations. This is the universal formula that I call the universal formula. Actually, S for me, I just call it that. So that is 1.4. So the first angle theta from our universal formula, that is the arc cos resistance over impedance. So that is arc cos the resistance of our circuit, which is 25, over the total impedance that we calculated here, which was 29.307. So just like that, you are going to obtain the phase angle, which is your theta, and that was going to be 31,456 degrees. Just like that. So with this, it is now for us to draw the phasor diagram. Draw the phasor diagram. We saw that if XL is greater than XC, it is mainly inductive. So we're going to have our diagram on top. This is what we saw on an RL circuit. We're dealing with everything above this. Okay? So you have to consider that. Why is that so? The current, it lags the voltage. So if the current lags the voltage, it means our voltage will be on top. So that's, you'll be considered that way. So there, is it you're considering the impedance or the voltages? It's up to you. So in this case, guys, I'm just gonna refer to the impedances. Okay, I have this impedance. I have my reactances here. All right, so I'm just gonna have it on this part. So the phasor diagram. So since in this case XL is greater than XC, that means we are talking of a more inductive circuit. So at the end, we just gonna have something like this. All right, so remember, just gonna use the impedances there. So this is gonna be our XL. Remember, XL is always on top. XC is gonna be down here. And there, you indicate the difference because XL is greater than XC. So you must indicate that XL minus XC, or you can even just indicate XL is greater than, or you indicate it with a minus to show that there we are going to use the difference. Remember, this is what I showed you guys there. We're going to use the difference of XL minus XC when XL is greater than XC. It is mainly inductive, so you must indicate that. Okay, then our total impedance there on top, which is now taken from that XL minus XE, but it's not necessary for you to be now showing it this side. No, that one is just for introduction purpose that I was just indicating. Just indicate your angle theta. Our theta, this is our Z. This is what we need. This is our resistance, which is just in phase with our total current. So we have got everything, guys. Remember our angle got 31.456. So this is 31.456 degrees. Okay. That is what we have. Our Z, the total impedance there, that's 29.307 ohms. The resistance of the circuit, remember resistance is 25 ohms from our diagram. That was 25 ohms. XC, we calculated our XC. There we got 31.831 ohms. XL, we calculated, we got 47.124. Just to remember here. That's 47.124 ohms. So indicating this is important because we need to know this is the one that is here, but you're not indicating there. Just write it like that. They will know what you are actually trying to say. So that's your phasor diagram. So let us keep on revising, guys, as much as we can. As we can see, there's nothing that has changed from what we had in our N3. As we are to consider our series RL circuit, we must consider these conditions and also any other possible condition that you might have, which is at resonance. And that one is going to talk about this on its own. So just try to revise. Maybe you might find another circuit which needs you to apply this condition where you see XC greater than XL. You use the same condition as what we're doing, only that you are going to be having this time our diagram down like that. In this case, we are simply indicating a condition that the current is leading the voltage. So meaning to say the voltage, this and that, is going to be lagging. So you indicate on your phasor diagram the difference XC minus XL. If it is voltage, it's going to be VC minus VL, and this will be the total voltage, and this will be our VR. So you must indicate all that. Is it from the voltages? Is it from the reactance? You work with what you need for the phasor diagram, or what you want, or what you are given according to the information. So we shall see again for an RLC circuit, but for a parallel now. So we shall see that on another class, so that we see the differences between this RLC circuit in series and when it is now connected in parallel. So that's for another class. Till we meet again.